The challenging and constantly changing environment of cybersecurity landscape need to be addressed with latest tools, approaches and architectures to combat cyber attacks and minimize or even eliminate vulnerabilities within information technology systems. The cybersecurity industry is more and more embedding data-driven algorithms in security software to detect cyber threats. Cybercriminals widely develop and use malware to attack IT infrastructures and systems, so one main focus of applied data science within cybersecurity is malware detection. A malware can be described as an executable program written with malicious purpose. This introductory lesson is created for aspiring data scientists who want to add cybersecurity-related projects to their portfolio. This lesson is also a good resource for cybersecurity professionals who are interested to apply data science within their daily workflows. In this project, we will build a robust binary classification model to detect malware based on portable executive header information datasets. The agenda is: First video episode, Introduction to Malware Types and Relevant Machine Learning Metrics. We will give you an overview of common malware types and relevant machine learning metrics for highly imbalanced data, which is essential for malware detection. We will also have a look on stratification methods and briefly have a look on imbalance learning as preparation for the second agenda item. Second agenda item and video is Malware Detection through PE Header Analysis. Purpose of this item to build a robust binary classification model in order to detect malware through PE header analysis. Relevant machine learning algorithms will be considered to build the binary classification model.
Malware analysis is a subject becoming more important recently. Companies worldwide are paying more attention for cybersecurity and defense mechanism. Allocated company budget planning and resources to defend cyber attacks expect to increase in the very near future. We would like to give you a brief overview of malware types and apply machine learning techniques to build a classification model. During the past years, malware attacks increased significantly worldwide. Attacks have been carried out on governments, companies, and individuals. There are many reasons for malware attacks, depending what in the cyber landscape needs to be harmed, destroyed, or hijacked. A precise approach for malware detection is gaining more and more significance for governmental instances, organizations, and private sector. There are many varieties of malware, and every day, there are new forms of malware that recreate previous methods of attack dynamically or implement radically new vulnerability tactics that leverage the specific characteristics of the target organization. Generally, it is possible to compile a classification of the most common types of malware in order to understand which are the most effective measures of prevention. So here you can see an overview of most common malwares. First, let's understand what a Trojan is. Trojan is a special form of malware usually disguised as software that is legitimate. As some form of social engineering, victims usually get tricked into loading and executing Trojans on their systems. Trojans will gain backdoor access to your device by cyber criminals and steal your sensitive data. Trojans can be, for example, keyloggers to steal usernames and password. Botnets are malware-infected computer networks and are typically remotely controlled by cyber criminals with the aim for financial gain or to initiate website or network assaults. A computer infected with this type of malware and part of a botnet will communicate and receive instructions from command and control computers anywhere around the globe about what it should do. What your computer is doing depends on what the cyber criminals are trying to do. Most botnets are intended to collect data like credit card numbers, social security numbers, telephone numbers, addresses, and other personal data. The word botnet is a hybrid combination of the words robot and network. Ransomware is a form of malware that accesses, blocks, and encrypts files from a victim and then demands that the victim to pay a ransom to get back the hijacked files. Cyber criminals use these attacks to try to get victims to click on links or attachments that appear legitimate but actually contain malicious code. Payment is virtually always the target, and the victim is forced to PGA for the removal of the ransomware, either by supplying a program that can decrypt the files. In order to enable access to a computer or software region, a rootkit, which is a set of traditionally malicious software, is used. The aim of a rootkit is to hide presence or existence of other software. Detection of rootkit is difficult because it can manipulate the software which is installed to detect it. As a detection approach, an alternative operating system, difference or signature scanning, and behavioral-based methods can be used. If the rootkit is embedded in the kernel, a deletion is very difficult and nearly impossible. It should be considered that the whole operating system needs to be reinstalled. Firmware rootkits require in most cases an hardware replacement. The word rootkit comes from root, a known in the Linux world. First step for a cyber attack by cyber criminals to install malware on the target device is through a downloader. After a downloader is installed on the target device, it will try to connect to a remote instance like several website, where additional files for download can be found or further instructions where to find additional download files. A downloader is a piece of code in order to download a malware on your computer. Therefore, the detection of downloaders is more difficult than bigger size of malware, and cyber criminals have an easy step to download different types of malware on the target device. Phishing is a cyber attack method where cyber criminals send random emails to a wide audience in order to manipulate users to send sensitive information like bank account numbers, account passwords, or login passwords. In most phishing cases, the user is fooled into following a malicious link, which may result in a malware download or disclosing sensitive information as start of a ransomware attack. As countermeasures to defend a device from malware attacks carried out by cyber criminals, malware detection strategies can be used like network management strategies, constant system monitoring, or hashing. A network management system continuously tracks a computer network for elements which are delayed or missing, and in case of anomalies or other issues, the network administrator is notified. Protocols are used to monitor network infrastructure. Through system monitoring, computer operations like RAM or CPU usage is measured, and in case of performance anomalies regarding software applications or hardware, the cause of problems could be identified locally or remotely. Simple code analysis tools can also be used for analyzing if code of a software application contains malware packages. Finally, another common technique to identify malware is hashing. In case a unique hash of software is determined, it can be used for different use cases. Sharing labeled suspicious bit of code and identifying if a malware has been detected within the malware analysis community is a huge benefit through hashing. Perhaps a suspicious bit of code has been already identified as malware among the malware community. Hash serves as a fingerprint of the malware to perform further searches in order to find out what information is available. Most common approaches for malware analysis is known as static and dynamic analysis of malware. I would like to give you a brief overview of what differentiates static versus dynamic malware analysis. Static analysis detects malware without running it. No deep dive of the code or instructions is scope of a typical static analysis. There are different tools and methods used to analyze if a file is malicious or not by disclosing information about technical indicators to define signatures. Technical indicators are checksum, file size, and type or hashes. Before executing assembly instructions in the disassembled binary image of the malware, external characteristics of the binary code reliability must be identified. Because of the immense presence of anti-analysis methods, this is not possible to be assumed. A preliminary analysis to detect packets which encrypt portions of executable code need to be done up front. Cyber criminals developing countermeasures to prevent malware analysis rely on using packets and payloads encryption. A dynamic software analysis approach is able to detect these obstacles. When using virtual machines, the presence of the virtual environment can be detected by advanced malware. Identifying anomalies in datasets and have an accurate classification is a difficult task. The most critical consideration is that the dataset is highly unbalanced. For our machine learning use case within the cybersecurity area, classification if malware is detected or not is critical to build a robust model. We can think about binary classification problems if we want to apply machine learning algorithms for malware analysis. So what we need to understand is the following question. What does an imbalanced dataset mean? A highly imbalanced dataset means that an unequal distribution of classes is reflected in the dataset. For instance, a real-world scenario is cancer detection. You have much more patients who have a negative cancer test relating to patients who have a positive cancer test result. In this example with the confusion matrix, the positive and negative values outlined in blue indicate that the classification model used to detect cancer as true positive and not detecting cancer as true negative values are realistic. But also test data which are incorrectly classified. Here, false positive and false negative will have a significant impact on the considered evaluation metrics and use case. First and foremost, let us see how precision is calculated true positive divided by actual results. Answer yes, or more in depth, addition of true positive and false positive, which is called precision. So with our cancer classification example, the final result for precision is 0.33. Generally, precision is a suitable indicator in case the importance of false positives is high and important to pay attention when evaluating our machine learning model. In our classifier, 10 patients who have not a cancer are incorrectly diagnosed with cancer. Well, this is shocking news for 10 patients. Within this case, further diagnosis will indicate more accurate results and the 10 patients will be happy because of the accurate results of the machine learning classifier. The other significant metric is recall, which is calculated by true positive divided by predicted results, or better by the addition of true positive and false negative, so in our cancer detection example it is 0.50. Recall is the important metric when we use to evaluate our machine learning model, in case a high cost is associated with false negatives. In our classifier, 5 patients who have cancer are incorrectly diagnosed without cancer. Recall is characterized as the predicted percentage of positive classified results out of all positive predicted results by the classification model. In our example, a total of 5 patients are correctly classified to have cancer out of all 10 patients who have actually cancer. In data science, the metric accuracy is in most machine learning use cases the key metric for evaluating the robustness of a machine learning model, but accuracy does not consider class imbalance within a dataset. The percentage of correct predicted results by the classifier out of all available test data is the metric that can be understood as accuracy. Incorrect predicted results from a minority class within an imbalanced test dataset are out of scope of the metric accuracy. In our example, the number of correct predictions divided by total number of labeled test data results in accuracy of the machine learning model. In our case, the accuracy is 0.90 or 90%. Another important key indicator evaluating machine learning models for highly unbalanced data is the F1 score. This metric takes both precision and recall into account. So what is the difference between F1 score and accuracy? False positives and false negatives are absolutely crucial and critical to our binary cancer detection use case with highly imbalanced labeled data, while true negatives is not as much important to predict. The machine learning classifier is able to predict that a patient has not cancer precisely and accurate. We need throughout the entire project to take into account that cancer detection is the main purpose to build the machine learning model. And our dataset is trained on a majority class labeled data from patients without having cancer, and therefore most likely overfitted to the majority class labeled data. The result of a data science project is to build a robust machine learning model. A robust classifier must be precise for all labeled test data, especially for minority class labeled test data. This is considered by the F1 score, which gives more attention to false negatives and false positives, considering correctly classified true positive results of the minority class, while not paying any attention to majority class labeled test data, classified by the model as true negative cases. In our example, the overall F1 score is 0.40. One of the most important scores for evaluating machine learning models for binary classification with highly unbalanced dataset is a balanced accuracy score. This score considers 2 metrics. First it is sensitivity and second it is specificity. So what does these 2 metrics indicate? Let us start by understanding what sensitivity score means. Sensitivity indicates how many of positive cases were correctly detected as positive within the total number of positive and negative cases. For our cancer detection example, sensitivity indicates the proportion of patients who have actually cancer and for whom cancer was also correctly recognized. Also known as true positive rate is in our example 1/3 or 0.33. And, yes, you are correct. Sensitivity is the same as previously shown the metric. Recall. Apart from sensitivity score, let us understand what false negative rate means. False negative rate indicates how many cases were incorrectly classified as negative within the total number of positive and negative cases. For our cancer detection example, false negative rate indicates proportion of patients who have actually cancer but diagnosed incorrectly as healthy, which is 2/3, or 0.67. Sum of true positive rate and false negative rate is always 1. The other important score is specificity. Let us understand what specificity means. Specificity indicates how many negative cases correctly classified as negative within the total number of negative and positive cases. Specificity indicates in our example the proportion of patients who have not got actually cancer and also correctly diagnosed without cancer, also known as true negative rate. In our example, the rate is 0.97. Apart from specificity score, let us understand what false positive rate means. False positive rate indicates how many cases correctly classified as negative within the total number of negative cases. This rate indicates in our example the proportion of patients who are actually healthy and incorrectly diagnosed with cancer. Sum of true negative rate and false positive rate is always 1. Finally, the balanced accuracy score is sum of sensitivity and specificity divided by 2. In our example, the balanced accuracy score is 0.65. Perhaps the most important metric for evaluating classification performance of machine learning models is with receiver operating characteristic curves. What does a plotted receiver operating characteristic curve indicate? It shows the trade-off between true positive rate and false positive rate across different decision thresholds. These thresholds are implicit and not shown as an axis. It can be assumed that the ideal decision threshold is set by 0.5 to separate true positive and true negative, as well as false negative and false positive frequency in a classification model. A random linear line from down left to upper right indicates the random classifier under R. The curve is above the random classifier line. For binary predicted probabilities, as already mentioned, a decision threshold by default 0.5 is taken to get a concrete loss prediction for a given sample. This means that in case a predicted probability is above 0.5, is considered to belong to class 1. The opposite belongs to a predicted probability, which is below 0.5, and the sample belongs to class 0. AROC curves start at false positive rate 0 and true positive rate 0, which is at the lower left-hand corner, where actually every example is classified as negative because all predicted probabilities are less than 1. The ROC curve always ends at the upper-hand corner with false positive rate 1 and true positive rate 1 and a decision threshold of 0, where every example is classified as positive because all predicted probabilities are greater than 0. The area beneath the receiver operating characteristic curve is called the AUROC curve. A and U stands for area under. The x-axis of the ROC curve is the false positive rate, and the y-axis of the ROC curve is the true positive rate. A URO curve is plotted between the true positive rate on a y-axis and false positive rate on a x-axis at various threshold settings. This curve is used how accurate the classification model is able to separate true positive and true negative. So perhaps you can start to understand with the ROC curve how your classifier performs as a so-called discriminator. The area under a receiver operating characteristic curve indicates the performance of your classification model. For instance, a value of 0.5 is equivalent to a coin flipping scenario, and generally this indicates not a good performance. A value between 0.7 and 0.8 indicates a good performance. A value greater than 0.8 is an excellent performance. Finally, a value of 1.0 indicates a perfect classifier by calculating the true positive rate and false positive rate for different thresholds between 1 and 0. the different points which create a ROC curve can be determined. In case more points are calculated, the ROC curve is a more smoother curve. Let us have a look on our classifier for cancer detection and understand how predicted probabilities are distributed among true positives, false positives, true negatives, and false negatives. As outlined in the confusion matrix, shown some slides before, here we can see that the binary classifier is using a probability threshold of about 0.6 as best outcome. Again, we would like to repeat some formulas behind this table. First, true positives and false negatives does have in every assigned probability threshold a sum of 10, due to the fact that the model classifies the minority class, cancer, yes second. True negatives and false negatives does have in every assigned probability threshold a sum of 155, due to the fact that the binary model classifies the majority class, cancer, no. For the ROC curve, it is required to determine the true positive and false positive rates. The approach to determine these scores have been already shown some slides before. Now, let us have a look on the synthetic created ROC curve. Please bear in mind that for this cancer example, we work with synthetic data in order to have an idea how to interpret all relevant score, metrics, and graphs. As previously mentioned, the key metric for the x-axis is the false positive rate. For our cancer detection classifier with highly imbalanced dataset, the classified majority class increases the true negatives to a huge distance comparing to other confusion matrix values. Therefore, it is not recommended to go a step further and start to find out the area under a the operating characteristic curve, due to the simple fact that the false positive rate with true negatives from the majority class is taking too much room within the relevant metrics in order to understand dependencies and evaluate our binary classification model. Considering the linear behavior of the ROC curve, this metric cannot be a reliable performance indicator for all machine learning classification use cases. For further investigation, it needs to be mentioned here that the true negatives are out of scope from two previously mentioned metrics, recall and precision. And now we would like to introduce you to our last classification performance indicator for machine learning models. The precision recall curve. At this stage, it needs to be underlined that precision recall curve is not taking true negatives, the majority labeled class in an imbalanced dataset, into consideration. Precision and recall scores have been earlier in this course with necessary details introduced. The precision recall curve is a plot of different probability thresholds and showing the relationship between recall or sensitivity on x-axis and the precision on y-axis. For imbalanced classification challenges, a fundamental question which need to be considered throughout the project need to be reminded. For instance, if a trained classifier is able to detect credit card misuse with high precision and rejects falsely claimed credit card misuse, rather than having a higher recall than precision and cannot detect consequently credit card misuse with high financial impact, but nearly does a good job in detecting legal credit card usage. Let us try to understand trade-off between precision and recall. A high recall and low precision means that your model is able to find all relevant instances in datasets, but cannot precisely classify them. A high precision and low recall means that your model is able to precisely classify a relevant dataset within all data, but not able to find all relevant instances in datasets. In this case, your classifier might be overfitted during the training with training data labeled as majority class. A perfect binary classifier for imbalanced data has a high recall as well as high precision with nearly zero false positives and false negatives. In case the probability of decision threshold of a classifier will be increased, precision score will increase due to decreasing number of false positives and recall decreases. So decrease or increase of precision may not in any case have impact with recall. In case probability of decision threshold for the classifier decreases, recall score may increase due to increasing number of true positives, but also recall can remain unchanged, while precision decreases. Comparing the precision recall curve to the receiver operating characteristic curve, we can conclude that the precision recall curve is more suitable to evaluate a binary class machine learning model for imbalanced datasets. If the positive class is the most important, then the precision recall curve and area under curve can be used. This will optimize both precision and recall across all thresholds. A relevant metric for area under curve for precision recall is the average precision score. So what can we understand as average precision score? AP summarizes a precision recall curve as the weighted mean of precisions achieved at each threshold, with the increase in recall from the previous threshold used as the weight. The average precision is precision averaged across all values of recall between 0 and 1. We will embed the average precision value as core evaluation metric to assess machine learning models within this course. So now I would like to give you a brief summary of what we have learned so far. Main purpose of this chapter was to get a basic understanding needed for future chapters, which will be focused on applying machine learning algorithms. I hope you have been able to get an accurate and basic understanding in terms of examples of malware analysis tools, types and species, interpretation of machine learning model evaluation metrics and their application for imbalanced classification problems. These items are needed to have a basic understanding for applying machine learning algorithms within cybersecurity items like malware detection. In general, you can apply your skills in terms of evaluating machine learning models for highly imbalanced for other topics like malware detection. Now we are ready and carry on our journey and apply our skills for building machine learning models for malware detection.